Pluto has long intrigued astronomers, and recent developments surrounding its orbit have captured even more attention. Once considered the ninth planet in our solar system, Pluto's status changed when it was reclassified as a dwarf planet due to its unique orbital characteristics. Despite its demotion, Pluto continues to fascinate both scientists and space enthusiasts. Recent statements from experts like Neil deGrasse Tyson and Michio Kaku have raised concerns about Pluto's orbit potentially crossing paths with that of Neptune. This has led to speculation about the potential consequences for both Pluto and the solar system. But how did Pluto end up on a path that intersects with Neptune? And what could this cosmic collision mean for life on Earth? Join us as we explore the possibility of an encounter between Pluto and Neptune, and why researchers are concerned about this cosmic anomaly. Pluto's journey around the Sun is unlike any other planet in the solar system. Its orbit is highly elliptical, with the distance from the Sun varying dramatically during its journey. At its closest, Pluto is about 30 astronomical units (AU) from the Sun, but at its farthest, it reaches nearly 49 Australian dollars, almost double Neptune's distance from the Sun. In addition, Pluto's orbit is tilted by about 17 degrees relative to the ecliptic plane, adding another layer of complexity to its path. One of the most striking features of Pluto's orbit is that it periodically crosses Neptune's path, a phenomenon that occurs for about 20 years during each orbit. Given these unusual characteristics, Pluto's interactions with Neptune have puzzled scientists. At first glance, one might assume that these two celestial bodies would eventually collide, but a closer look reveals that the situation is far more complicated. Despite their orbits crossing, the gravitational forces at play prevent an actual collision from occurring. The two bodies' paths are carefully orchestrated by a complex gravitational dance, ensuring that Pluto and Neptune avoid a catastrophic impact. How is this possible? The answer lies in a phenomenon known as orbital resonance. As Pluto and Neptune interact gravitationally, their paths are locked in a way that maintains stability. This resonance keeps Pluto's orbit from deviating too far from its established path, despite the periodic crossing of Neptune's orbit. This intricate dance of celestial mechanics ensures that even though Pluto and Neptune come close to each other at times, they never collide. Recent advancements in observational technology have allowed astronomers to track Pluto's movements with incredible precision. This has led to a deeper understanding of its orbit and its relationship with Neptune. While the possibility of a direct impact between the two remains extremely unlikely, the gravitational interaction between Pluto, Neptune, and other celestial bodies in the outer solar system is still an area of intense study. The stability of Pluto's orbit continues to be a subject of interest among astronomers, especially as they seek to understand the long-term behavior of objects in the distant reaches of our solar system. So why hasn't there been a collision between Pluto and Neptune? The answer lies in the complex mechanics of their orbits. When Pluto crosses Neptune's path, they are positioned in such a way that their gravitational forces work in harmony, preventing an impact. This is where the concept of libration comes into play. Libration refers to the way in which the two bodies' orbits remain stable even when their paths cross. In essence, when Pluto approaches Neptune, it is always at least 90 degrees away from Neptune's position, ensuring that the two bodies are never on a collision course. Further, the concept of VZK wobbling, named after researchers von Ziel and L., explains the apparent irregularities in Pluto's orbit. Despite the seeming chaos of Pluto's path, its orbit remains remarkably stable over time. This wobbling effect ensures that Pluto's interactions with Neptune remain predictable, preventing any drastic changes in its orbit. The question then arises: if Pluto's orbit is so unstable, why does it remain stable over billions of years? The answer lies in the finely tuned nature of celestial mechanics. Even small changes in Pluto's position or velocity can have significant long-term effects on its orbit. Yet, despite the complexities, Pluto's path remains consistent due to the gravitational forces at play. The study of these interactions, using sophisticated computer simulations, has allowed scientists to model the future of Pluto's orbit with remarkable accuracy. In the 1980s, astronomers began using advanced simulations to study Pluto's orbital behavior. These models showed that although Pluto's orbit is influenced by many factors, it remains relatively stable over the long term. Even small changes in its orbit can result in large variations over time, but these variations tend to balance out, ensuring that Pluto's orbit remains consistent for billions of years. While predicting the future behavior of planets with eccentric orbits is challenging, these simulations provide valuable insights into the mechanics of our solar system. They show that even in the chaotic environment of space, patterns emerge that allow us to understand the long-term behavior of celestial bodies. However, the inherent unpredictability of these systems means that we can never be entirely certain of what the future holds. In conclusion, Pluto's orbital path, though highly irregular, remains stable due to the gravitational interactions between it, Neptune, and other bodies in the outer solar system. Despite the apparent chaos of its orbit, the forces at play work together to ensure that Pluto and Neptune avoid a collision. While the possibility of a direct impact is extremely low, the fascinating interplay between these two distant planets highlights the intricate and dynamic nature of our solar system. Emphasizes the vast potential of studying Pluto's orbit, suggesting that insights gained from it can be applied to understanding other celestial bodies, offering a roadmap for exploring distant universes. He frequently underscores the profound connection between cosmic mechanics and theoretical physics, pointing out that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are rooted in fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, seeks to unravel these principles at their core. He proposes that examining the complexities of cosmic mechanics, like Pluto's orbit, can provide valuable insights into the underlying laws of the universe. Similar to Tyson, Kaku has also speculated about potential cosmic collisions, connecting these ideas to his theories on the nature of the universe. A collision between Pluto and Neptune, while significant in astronomy, could present a fascinating observational opportunity, possibly contributing to our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, aims to describe the fundamental forces and matter in the universe. Such a collision could generate extreme states of energy and gravity, offering valuable data on how fundamental particles and forces behave under intense conditions. Additionally, the gravitational waves produced by such an event could provide crucial information to test string theory's predictions regarding gravity and spacetime. While the direct impact on Earth would be minimal due to the distance from our solar system's outer boundaries, the scientific implications could be profound. Understanding such events could expand our knowledge of the universe's fundamental nature, as described by string theory and other branches of theoretical physics. Pluto's unique characteristics, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the intricate and dynamic nature of space. Yet, the universe holds countless secrets, and the three-body problem is just one of them. Scientists anticipate other potential cosmic catastrophes, underscoring the ongoing quest for understanding and exploration in the vast universe. Although the likelihood of planetary collisions is extremely low, the complex gravitational interactions between planets can lead to unexpected outcomes. The three-body problem, a phenomenon where planetary orbits are influenced by the gravity of other bodies, provides insight into how planets move through space. For example, in systems like TRAPPIST-1, where 7 Earth-sized planets exist, the gravitational forces create orbital resonances that can destabilize planetary paths over time, possibly leading to collisions. While no such impacts are occurring currently, scientists continue to monitor these systems to understand how planets influence each other's orbits, particularly when they come into close proximity. Additionally, there are rogue planets that no longer orbit a star and drift aimlessly through space. These planets were once part of a star system but were ejected due to gravitational interactions or a nearby star's influence. Over time, these rogue planets can travel vast distances and potentially collide with other star systems. However, the vastness of space makes such collisions exceedingly rare. Rogue planets present an interesting subject of study compared to the number of stars and planets with stable orbits. Collisions between planets are even less likely during galactic mergers, where the gravitational forces can alter the orbits of stars and planets. During these events, planets might be ejected into space, collide with other celestial bodies, or even with their host stars. These disturbances could lead to the formation of new solar bodies or even new stars. The heavy bombardment theory suggests that about 4 billion years ago, our solar system experienced a period of intense collisions involving comets and asteroids. This surge in impacts is believed to have occurred as the outer planets like Jupiter and Saturn moved, disrupting the paths of smaller objects in space. As a result, many of these objects were ejected into erratic orbits, some of which brought them into the inner solar system, leading to increased collisions with planets like Earth. While these collisions didn't involve planets directly crashing into each other, they demonstrated how gravity could drastically change the motion of objects in space. Scientists believe this bombardment played a significant role in shaping the surfaces of planets in our solar system, potentially even bringing water and organic compounds to Earth, helping shape our planet. As stars evolve, they lose mass, which can affect the orbits of surrounding planets. Sometimes this can cause planetary orbits to expand or even overlap. This change is most noticeable in star systems nearing the end of their life cycles. As a star ages and depletes its nuclear fuel, it undergoes significant mass changes, particularly during phases like the red giant stage or when it sheds material in a planetary nebula. These mass variations can greatly impact the gravitational equilibrium of the system, causing nearby planets' orbits to shift, sometimes moving outward or becoming more compact. This phenomenon is more common in multi-star systems, where complex gravitational interactions can lead to unstable orbits, increasing the chances of planetary collisions or other disruptions. The gravitational forces from multiple stars can interact in unpredictable ways, making orbital shifts more likely. This could lead to situations where planets are captured by another star, collide with other celestial bodies, or are flung into interstellar space. Although the chance of a planet colliding with another is considered highly unlikely due to the vastness of space and the relatively small size of celestial bodies, these scenarios are of great interest to astronomers and astrophysicists. They provide insights into the dynamics of planetary systems and the evolution of worlds. The ongoing study of Pluto's orbit exemplifies the relentless pursuit of knowledge in space exploration. As Tyson and Kaku have illustrated, every discovery brings us closer to understanding the complex nature of our universe. This journey challenges our perceptions, broadens our horizons, and inspires future generations of explorers and scientists. Pluto's orbit is significant, especially when we consider the possibility of a future collision with Neptune. This information helps us better understand how our solar system functions. Pluto's orbit demonstrates how seemingly irregular orbits can stabilize due to gravity and how objects move in space. It's crucial to continue observing and studying these phenomena to understand our place in the universe. When we explore space, we realize that things can be unpredictable, and Pluto's orbit serves as a perfect example of this unpredictability. Unlike the orbits of other planets, Pluto's path is more oval-shaped, meaning it doesn't follow a perfect circle. Sometimes it even gets closer to the Sun than Neptune does. This can create some concerns since Neptune is also moving along its orbit. While there is a small chance that Pluto and Neptune could eventually collide, their orbits are carefully regulated by gravitational forces. Gravity is an invisible force that pulls objects toward one another, and although Pluto and Neptune might seem like they're on a collision course, their orbits are actually in a delicate balance due to gravity's influence. Pluto's orbit teaches us that space is full of surprises. What seems chaotic at first may actually be a delicate equilibrium of forces. By studying Pluto's orbit, scientists gain insights into the complex mechanics of our solar system, and continued observation and research are vital for expanding our knowledge of the universe and our role in it. Imagine if Pluto and Neptune did collide. It would be a monumental event, shaking up our understanding of the solar system. Despite the progress we've made in understanding space, this scenario shows that there's still much we don't know. Studying how large planets affect Pluto's orbit provides valuable clues about how our entire solar system operates. It shows us that the position and motion of each planet can influence the paths of other objects in space. Though space is intricate, many leading scientists are concerned about the potential for Pluto to collide with Neptune, prompting them to ask why this might happen. Although a collision seems unlikely, renowned astrophysicist Neil deGrasse Tyson has some intriguing thoughts about Pluto. He believes renaming Pluto as a dwarf planet, rather than a full-fledged planet like Earth, is a positive step. Tyson is fascinated by Pluto's unusual orbit, seeing it as a reminder that there's still much to learn about space. He believes that the mysteries of the universe are what makes studying space so exciting. Tyson emphasizes the importance of understanding how space works, pointing out that its complex mechanics can often surprise us. Working with other scientists, Tyson warns people about the potential risks of Pluto's strange orbit, noting that a collision with Neptune could have serious consequences for the entire solar system. A collision between Pluto and Neptune would be a dramatic and dangerous event, releasing vast amounts of energy. Debris from Pluto could scatter throughout space, possibly colliding with other planets and moons. Neptune might also be affected, potentially altering its orbit. The prominent theoretical physicist Michio Kaku, known for his work on string theory and his ability to communicate complex scientific ideas, offers a unique perspective on space exploration. He believes that understanding phenomena like Pluto's orbit can provide insights into the future of space travel and the relationship between celestial mechanics and theoretical physics. Kaku sees Pluto's orbit as a window into the future of space exploration. By understanding the intricate gravitational interactions and orbital dynamics of bodies like Pluto, we can improve future space missions and navigate the solar system more safely. This knowledge allows us to anticipate potential hazards and plan missions to the far reaches of our solar system more effectively.